This video goes over the 4.0 practice for Unit 7, and I'm not going to do every question, so follow along, and you are to do the ones that I do not do on here. So first of all, this method that we're going to be talking about is called linear programming, and it's only one step further than the method that we've been doing in class. The feasible region is formed by the graph of the system and the vertices of the solution set. I just realized I forgot one of these blanks. Linear programming is a method for finding maximum or minimum values of a function over a given system of inequalities, with each inequality representing a constraint, which we've already talked about. Okay, so take for instance this one. This is a good example to do because they're nice lines. I'm just going to let each tick mark be 1. Okay, so x is less than or equal to 6 is a vertical line through 6. And it's going to be less than or equal to, so it's going to be shaded to the left. Y is greater than or equal to negative x plus 10. So I'm going to start at 10 and go down 1, right 1. And since it's already solved for y, I'm just going to do that all the way across. And that is also a solid line. And then y is less than or equal to x plus 2. So I'm going to start at 2, and I'm going to go up and right. And that's less than, so we have a solid line. Kind of changed colors, sorry. So we're looking at a space that is less than the vertical line, greater than this line, and less than the blue line I just drew, and we're looking at this space right here. Now that is going to be our feasible region. And so within that feasible region, we're looking at the vertices. So we're looking at the point 4, 7, 6, 4, and 6, 8. And I just realized I actually misspoke here. This should be 4, 6. So do 4, 6. Okay, so now I'm going to take each one of these numbers, I'm going to plug it into my objective function right here. And so I'm plugging in the x for x and the y for y. And so this is negative 40 plus 30. That's going to give me negative 10. This is negative 60 plus 20, so that's negative 40. And negative 60 plus 40, that gives me negative 20. Okay, so my minimum value here is going to be negative 40, and my maximum value is going to be negative 10. And you're going to do the exact same thing for question A on the next page, or on the back of that page. So go ahead and do that, and then use the answer key up front to check yourself. So now let's look at this example, and I'm going to kind of walk you through an entire one of these, and then you'll have a few that you can do for it as well. Okay, so the first thing that you have to do is you have to read through, identify your variables, and identify your constraints. So we have an area of a parking lot is 600 square meters, and we have cars and we have buses that are parking. And so I'm going to let cars be x and buses be y. And so a car requires 6 square meters, so we have 6x. A bus requires 30 square meters, so 30y. And we only have 600 feet, so less than or equal to 600. It also says the attendant can handle only 60 vehicles, so the total of buses and cars has to be less than or equal to 60. Now, we're trying to achieve maximum income, so our objective function is going to be a profit function, and it comes from $250 per car and $750 per bus. Okay, so now I need to go ahead and I'm just going to kind of talk through a couple of things here. So I want these graphs to be as good as possible because I want to be able to figure out where they're intersecting based on the graph. And so I'm going to start by finding my x and y intercepts. And so, for instance, my x-intercept here is 10, or 100, sorry. And my y-intercept would be 20. So x-intercept 60, and remember, I'm just getting that by doing 60 divided by 1. And so on that first equation, it was 600 divided by 6, 600 divided by 30. I don't graph my profit, so these are my only two restraints that are getting graphed. And so I'm going to let each one of my tick marks go by 20. So I have an x-intercept of 100 and a y-intercept of 20. Now I want this line to be as close as I can get it. I want it to look good. And so I'm just going to try to draw that as straight as possible. So if you have a ruler, it might even be good to get a ruler. Okay, that wasn't very straight, so hopefully this will work out. Let me try that again really quick. It's hard to do on the iPad. We'll go with that. We'll make it work, and I'll show you what to do. Okay, so then our x-intercept on the other one is 60, and our y-intercept is 60. And this one has a slope of -1, so it's a little bit easier to get that to go straight down like we want it to. Now, these are both less than, so they're intersecting right here. And so I need to know the vertices of this feasible region. So here's one, that's an easy one, that's just 0, 20. Here's one, that's 0, 0, 60, 0. But I need to know this, and I need to know that exact point. It looks like 50, 10. So you could plug in 50, 10 and see if that works. But remember how to find the intersection of a line. We spent a whole unit on it a couple units ago. We have elimination, we have substitution, we also have graphing, but our graphing isn't giving us an exact answer here. So what I can do is I can take this system and I can actually solve it using like elimination, for instance. So I write down my system. As you remember, I like elimination. It's my favorite method. So I'm going to eliminate my x's. I'm going to multiply this bottom equation by -6. I'm just going to copy this top one over. And I'm going to multiply everything in the bottom by -6. And then I'm going to add them together. The x's cancel. (24y) equals 240. Divide both sides by 24, so y equals 10. Now I'm going to plug that into like this equation right here because they have to equal 60 when they add up, which means that x has to equal 50. So pretty close on my graph to 50, 10, but I'm glad that I checked it just to make sure. Okay, so I have these 4 vertices, and I'm looking for the profit at each one. So I'm going to just, for my notation, and this isn't anything special, I'm just going to say my P, my profit at 0, 0. Well, that's $0. I'm not making anything. My profit at 0, 20. So that is 20 times $7.50. So that's $150. my profit at 50.10, that's 250 times 50 plus 750 times 10, so $175. And then my profit at 60.0 is 250 times 60, so 150. So what's giving me my maximized income? Well, 50 cars and 10 buses would do that. And so that's going to be my answer. 50 cars, 10 buses. So we looked at all of those constraints and we looked at what we were trying to maximize. We graphed our constraints, we found our feasible region, we identified our vertices, and then we plugged those vertices into our profit objective function. Now, I went back and checked myself just to make sure that I did this correctly, and I realized I had one little, I just misspoke here. This profit at 50.10 should have been 200. It was 125 plus 75. So still the maximum profit of $200. Just make sure that you always go back and check and make sure that everything makes sense. And so that fixed that problem. Okay, now look at the next couple of examples, and I want you to do those, and then I want you to check the answers on the answer key. So you're writing the objective function, and you're finding that feasible region, and you can see on this one, we're talking about bikes. And here we're talking about a sporting goods store. So just try these problems out and then check them versus the answer key. Just write those objective functions just like you did at the 3.0 level, and then take it that one step further with the feasible region.